Hello students, welcome to the introduction of the MEC04 Simple Harmonic Motion. This is part of the introduction for the fundamental labs at the Department of Physics and Material Science, Chiang Mai University. So today we're going to explore what we call the Hooke's Law. And the Hooke's Law was named after Robert Hooke, a mathematician who came up with the fundamental law of the spring. So for a spring, when you have a spring, it starts at equilibrium, but however, when you pull it out of the equilibrium with a displacement vector x, an opposite force F equals minus kx is being acted on. That means the more you displace the spring further, the force of the opposite direction would be acting on it with a multiplier of the spring constant, which is called the Hooke's constant. Okay, so k is the Hooke's constant or the spring constant. So naturally, force is in the unit of Newton. So the spring constant is going to be in the unit of Newton per meters. And then x is the displacement from the equilibrium point where the spring is neither stretched or pushed over. And the unit is in meter. So today we're going to test up Hooke's law and the consequence of it. And we would have what we call the spring mass system. So if we hang a mass on a spring and we disturb it by pushing it further away with a distance x, then it's going to cause the restoring force, pulling it backward. However, if the mass is pushed too far, the force goes the opposite direction. So it creates an oscillation, and this oscillation is called the simple harmonic oscillation, just like in this picture. So if you have like a spring mass system, basically if you disturb it, it would create an oscillation like this, and it follows a sinusoidal motion, which you can see. So how does this evolve, you may wonder? It's a solution of what you call ordinary differential equation, which is not a big detail that you need to go into solving. However, it goes like this. You have sigma force equals ma, and then since the force you have is the displacement from Hooke's law, and you can put the acceleration term in terms of m d2x by dt squared. And then if you move the terms m here, you get the minus k over m times x equals d2x by dt squared based on this relation. And then if you assume that the motion of the x is actually a sinusoidal motion, which this is what we call a simple harmonic motion, with an angular frequency of omega times t plus phi, whatever phase it is. So if you would like to solve this equation, you need to differentiate x twice. So if you differentiate it once, an omega come out, and then the cosine becomes minus sine. And then if you differentiate it once again, another omega comes out, and then the sine become cosine. So here is where things get a little funny, because the a cosine omega t plus phi is similar to this x. So this entire term can be called x. So you know that d2x by dt squared, if it's a simple harmonic motion, whatever is being multiplied there in front of the x and the minus here, that constant is omega squared. And if you look at this equation that you can derive from Newton's equation of motion, you can compare the k over m to omega squared. So these two terms must be the same. So you can come to a conclusion of omega equals squared k over m, which is the equation that you learn in the lecture. So the unit of this omega is called the angular frequency. It means how many angles of the rotation the simple harmonic motion goes through as a radian per second. So from this information, you can start working on the lab. So the first thing you need to do is to test Hooke's law. So by testing Hooke's law is you're going to be putting a hanger right here and then put a weight on it. So this weight would act as an mg, the force that is pulling the spring from the equilibrium. So the spring will stretch out with a distance x that you can read from the scale over here. And in response, the spring would try to pull it back with the force on the exact opposite direction of the displacement x down there. So this force has to be equals mg. So you know the relation that mg and kx are the same based on the lap direction. And And then you're going to try to make an oscillation out of it by oscillating this thing and then measure the period of the motion. Since omega is angular frequency, so angular frequency is square root k over m. By inverting the equation and telling all the mass, you can get this equation which relate the period with the k. So basically, if you square this equation, you can get t squared equals some complicated form divided by k here. So if you change the mass of the oscillation right here, so this m is the mass of the weight that's being put on top of the plate. mp is a mass of a plate, and ms is the mass of the spring. And it might be a little bit counterintuitive, but the mass of the spring is contributing to the total mass with a factor f, which you need to find in this lab. So anyways, the variable that you're going to be varying is m. So you change the weight that's being hung on here and then make a plot of t squared, which is the variable that follows whatever mass you put on. So you can actually find k from the slope of the relation between t squared and the mass. And then you can find f, which is the factor that the spring mass is contributing to the total mass. So again, you will make an oscillation like that, and measure the period, change the mass, and by changing the mass, you would get different data point on the t squared. Make this plot of t squared versus m, and then find the slope and find the y-intercept of this graph. Using the slope, you can find k, and once you know k, you can find the intercept point of this graph and use k and mp and ms to calculate the f, and that's the end of this lab. Okay, so please do enjoy the lab. Thank you.